Hello, this is John Burke. I am a visiting lecturer at Reseba, and this video follows up on my recording of yesterday where I talk about Bitcoin mining. I just want to clarify a couple of points that I think are important. So the first thing is I want to talk about hashing. So hashing is an algorithm that takes a specific input, can be arbitrary length, and produces a fingerprint, or what you might say is a fixed length character set, depending upon the type of hashing algorithm that you're using. So the result of hashing is called a digest, a checksum, a fingerprint, or simply the hash. And you use the digest, which is the output, to make certain that there has been no change in the original input. So for example, let's say my input is hello, and I run it through a hashing algorithm, and the hashing algorithm will produce a fixed length deterministic set of characters. If I change anything about that input, for example, I capitalize the H, or I misspell hello, I use one L instead of two L's, the digest, the output of the hashing algorithm, is going to be significantly different. So this means that I will know that the input has been changed and it doesn't verify, or it doesn't correspond to the original digest. I know that something has been altered. So real world hashes require four elements. It's infeasible to produce a given digest. So if I have a digest, how am I possibly going to produce that digest from a particular input? It's not going to be possible. It's also going to be impossible to what you might call reverse engineer the original message. There's no way I can start off with the digest and get back to the original message. It's going to be it's probably not, theoretically impossible, but it's going to be practically and economically impossible. The other requirement is that a small change in the input should result in a very, very significant change in the digest. And the result always should be of a particular fixed length, no matter the length of the original input, whether it is a single word, whether it is a chapter from a book, or whether it's an entire book. I will still get the same fixed length digest depending upon the hashing algorithm I am going to use. Now, one of the ways I can demonstrate this is simply by going to a hashing demo. So let's try it. Let's go to a hash demo 256, and we can, let's say, take this, and here we have input. I hope everyone can see this because this is the first time I'm using this particular software. But all right, so I'm going to put my name is John, and we see the output. Now I am using SHA-256, which is what the miners are using. Of course, I misspelled my name, so let's correct the misspelling. So let's go to John. You can see that the output is completely different. It's called the avalanche effect. All right, so what does this have to do with mining? Well, mining, they use this hashing algorithm, but what is it that they are exactly hashing? and I talked about this yesterday, and I may be incorrect as to some detail, but I am not incorrect as to concept. So what they have to do, of course, is they must assemble or prepare their block. So the main thing about the block is that it's containing transactions, and those transactions, of course, have to be verified and validated. They also have to be, as I said yesterday, they have to be compressed because we want small data files. And for this, we use a Merkle root, which we might say is the fingerprint of all of the transactions that are held within this block that has been put together by the miner. Of course, the miner also has to create the block header, which is a summary of the block's contents. It also has to have the hash of the previous block that is going to be in the header. Why is that important? Because of the very nature of the blockchain. We're trying to link two blocks together. Another very important element of what you're putting into your block is your potential block reward. Because if you were to leave out the block reward, how in the world are you going to get it if you happen to be the miner who will meet the requirements of the target value that is being set by the Bitcoin protocol, or in fact you get a value that is below the target value? Now, how do you get this target value? Well, you get the target value by using numbers over and over again. You use iterations and iterations of initial values of the nonce. If the original nonce doesn't work, I keep amending it and amending it and amending it, and I am running it through, massive CPU power and using immense amounts of electricity, trying to reach this target value or something below the target value. And so let's assume that, yes, I am the first miner to reach this target value, or I'm the first miner to produce a value below the target value. I announce this to the rest of the nodes that are on the network at that time. And so how can they check whether it's not a solution, but whether my input is correct? Because I tell them what the input is. I say, this is my input. You put this input, you run it through the SHA-256 hash algorithm, and you're going to get the target value or something below the target value. Therefore, I've shown you that I have met the requirements of the Bitcoin protocol, which should entitle me to a block reward. And my block reward is already built into my block, which will then be sent to my address as I've described previously, my Bitcoin ontology presentation. And this is how mining works. Now, I could have missed, a certain detail about, exactly what fields are being hashed in the block header. But for purposes of the course at Reseba, and I think for purposes of understanding conceptually what miners are doing, I think this is sufficient. And the other thing I want to say is that when you're reading all of these articles about what miners do, none of them are written by miners. They're written by people like me who are trying to find out what miners do. So you're constantly reading different articles, and sometimes you're reading articles that are absolutely wrong because they're trying to say, oh, you're solving some sort of cryptographic puzzle. No, you're not solving any cryptographic puzzle. You're trying to just, by brute force, run immense amounts of numbers through CPUs to try to get to this target value or something that is below the target value. And as I said yesterday, these target values are constantly changing so that we keep this consistency of producing about one block every 10 minutes. And of course, these blocks are then linked by the hashes. So, yes, when I prepare a new block, to be added to the longest chain, I'm going to have the hash of the previous block. When I solve this target value, my block will now have a hash. And the next block will then use my hash, which will be the previous block, which will be part of what is going to be hashed in order to produce the new block. And of course, it will have different transactions, and it will have the miner's reward stated in there, and so on and so forth, the Merkle fields. And this is the way the blocks are then chained together into the, and of course, according to Satoshi Nakamoto, it is the longest chain that wins. Why? Because it demonstrates that this is the chain where the most work went into production of the chain, the most expenditures of CPU power, electricity, and so on, have produced this longest chain, and this is the one that we are going to consider valid. So I hope I've clarified some of the points that I made yesterday, and knowledge is endless, and I'm going to continue to try to improve my knowledge of this process. But I think conceptually I've got it. And as I said, and someone can send me a link, if you can find an article that's actually written by a miner who's telling you exactly what they're doing at every step of the way, I am open ears. But this is not what you find when you look at the literature that is available on the internet, or when you look at the literature that's even available in books. So having said that, I will finish my recording for today, and I will see you soon. I hope I have at least clarified some things for you and have deepened your knowledge about mining. So goodbye for now.